In this diagram, we have three circles. Now, I will label the radius of the bigger circle. So the center here is O, and then I'll label here as A. So the radius of the bigger circle is OA. Now the second one, I'll label it as A1. And then the third circle as A2. Now you can see that the radius of the three circles are corresponding. They have corresponding size. Then I will also have from the point A, I will have another point B here. As you can see, a straight line. And then I'll have B1 here and then B2 here. You also see that line AB also corresponds with line A1, B1, and then also with line A2, B2. What that means is that we can say one triangle, they are forming right angles. One triangle is an enlargement of the other, or we can say similar, because they have equal angles and then they have corresponding sides. Okay, so we see the triangles teased out like this. So the indications of the right angles are here, like this. Now, because they have a common angle, and please note, they have a common angle. So with a common angle, it means that if I take, and the triangles are similar, which also means that corresponding sides, the ratio of corresponding sides are equal. So if I take a side opposite the angle, so AB, this side is opposite the angle, divided by the longest side, which is the hypotenuse, OA. It should be the same. This ratio should be the same as that of the second triangle. So A1, B1 divided by OA1. And it should be the same for all the triangles. That gives us a constant which we call sine in mathematics. So that is what sine is. It is a ratio of the side opposite an angle, and that angle is the angle other than the right angle, the 90 degrees angle. So we take an angle and then the side opposite that angle divided by the hypotenuse. It gives us a ratio that is called sine. So sine is a ratio of the side opposite the angle divided by the longest side, which is the hypotenuse. Now when you take, so I will label here as the opposite side. And then this side as the adjacent side. And then I have my hypotenuse, which is the longest side. Okay. Now the second one is I will take the adjacent side divided by the hypotenuse. So if I take OB divided by OA, this one should also be equal for all of them. So let's say OB2 over OA2, they should be equal. And that is the side adjacent the angle divided by the hypotenuse. It also gives us a ratio which is called cosine. And then there is another ratio if I take the opposite side divided by the adjacent side. So taking opposite side divided by the adjacent side. That gives me the tangent. So these are the trigonometric ratios that we have. Okay, so we have learned that for a right angle triangle, if you take the angle here, the side opposite the angle divided by the hypotenuse will give us a ratio which we call trigonometric ratio. Okay, so now with our trigonometric ratios, we have sine, we have cosine, and then we have tangent. These are not all, but these are the basic ones. We have the inverse trig ratios, so inverse of sine, inverse of cosine, inverse of tangent. We will talk about them later. Now sine is shortened as sin, cosine is shortened as cos, and then tangent is shortened as tan. So these are the short forms. So when I write them, you should be familiar with them. Okay. So when we take sine of the angle, it is opposite over hypotenuse. Then when you take cosine of the angle, it is adjacent over hypotenuse. And then the tangent of the angle is opposite over adjacent. So these are the basic trigonometric ratios we have. Given the right angle triangle here, with this side as x, this side as y, this side as x, and this side as r, if we want to divide the various sides among themselves, we can have r y over x over r. We can have x over r, and we can have y over x. We can also have r over y, r over x, and then x over y. All these 6 divisions, we can have them. Now, if you remember, we said sine of the angle gives us y over r. So that takes care of the first one. Then cosine of the angle gives us x over r. That also takes care of the second one. We have tan of the angle, which is y over x. This also takes care of the third one. Now, if we observe carefully, we can see that if I have 1 over tan theta, that is going to be 1 over y over x. Is that not so? And when I simplify, I'll get x over y. So we will say that this is the inverse of tan. So if you see x over y, it is the inverse of tan. Now let's apply it to r over x. That's the inverse of cosine. And then r over y is also the inverse of sine. Are we good? And so we have other trig ratios, and this we normally call them the inverse trig ratios. The inverse trig ratios, we have cosecant which we shorten as cosec. We have secant, and then we have cotangent. So these are the inverse trig ratios. Now cosecant, which is shortened as cosec of the angle, is equal to 1 over sine theta, and that is going to give us r over y. Then the second one, secant, which is also shortened as sec of the angle theta, is also 1 over cosine theta. And this, if you remember, cos theta is s over r, so the inverse will become r over x. And then you have the cotangent, which is also shortened as cot. So cotangent of theta is 1 over tan theta. And this is the same as cos theta over sine theta. And that gives us x over y. The diagram we see here is a circle with radius 1 unit, and so we call it a unit circle. For a coordinate x, y here, it means that the length from the origin here to this point is x, and then the length from this origin, also the origin here to the top here, is also y. Okay, but why have I replaced cos theta and sin theta with xy? I am explaining. Now, using the angle, sine of the angle is equal to opposite over hypotenuse. So in this case, our opposite is y, and then our hypotenuse is 1 unit. So any number divided by 1 is the number itself. So sine theta is equal to y. So in place of y here, I have put sine theta there. Okay, so that is why it is not y but sine theta. Then if I take cos theta, cos of the angle, it gives me adjacent over hypotenuse, which is x over 1. And that's cos theta is equal to x. So the x here is also replaced with cos theta. So I can clean the x and y and then replace them with sine theta and then cos theta. I hope this is understandable. Okay. That said, if I tease out the triangle, like this, so it's a right angle, and then I have my angle theta here. So this side is sine theta, this side is cosine theta, and this one is 1 unit. Now I want to apply the Pythagoras theorem. If you remember, it says the longest side. So let me say A, B, C. Let me label them. So AC squared is equal to AB squared plus BC squared, right? This is the Pythagoras theorem. Okay, so now for the length AC, we have it as 1. So 1 squared. For the length AB, we have it as sine theta. And then for the length BC, we have it as cosine theta. So we have here as sine squared theta plus cosine squared theta. So this is our first trigonometric identity. So we take note of that. Now, from the Pythagorean identity, we also try to see if the same identity can come in different forms. So this same identity, as you see here, can come as cos squared theta is equal to 1 minus sine squared theta. So it's just a rearrangement or making one the subject. So in case you have 1 minus sine squared theta, in case you have this expression, you may substitute cos squared theta for it. You get it? So, and then vice versa. If you also have this expression cos squared theta, you can change it to 1 minus sine squared theta. So another way this may appear is also sine squared theta is equal to 1 minus cos squared theta. So it's very similar. So we can rearrange them to appear like this as well. Okay. We will now try to develop other identities from the Pythagorean identity. So what we will do next is to divide through by cos squared theta. So we have cos squared theta already divided by cos squared theta. Then we have sine squared theta also to be divided by cos squared theta. Then 1 divided by cos squared theta. So sine cos squared theta divided by cos squared theta gives us 1. Sine over cos gives us tan. So this one is tan squared theta. And that will give us, so 1 over cos squared theta, that gives us sec squared theta. So this is the second identity we have. And this identity, just like the previous one, can also appear in different ways. So we can have it as 1 plus tan squared theta is equal to sec squared theta, which we have already seen. And then I can group like terms and then say that 1 is equal to sec squared theta minus tan squared theta. And then I can also regroup and say tan squared theta is equal to sec squared theta minus 1. So it can appear in any of these three forms. So that if you have 1 plus tan squared theta, you can substitute sec squared theta for it. And then in similar situation, when you have sec squared theta minus tan squared theta, then you know that this whole thing is 1.
and then you also look at this one. So you take note of the identities. We will continue by this time we are going to divide through by sine square theta. So we have it like this. Sine square theta cancels sine square theta, that gives us 1. Cos square theta over sine square theta is a reciprocal of tan, and a reciprocal of tan is cotan. So that will be cot square theta plus 1 is equal to, so 1 over sine theta is cosecant, so cosec theta, so cosec square theta. So this is the next identity we should note. Okay, and as usual, this may also appear in different ways. So we have cot square theta plus 1 is equal to cosec square theta, and this we can regroup as cot square theta is equal to cosec square theta minus 1. We can equally write it as 1 is equal to cosec square theta minus cot square theta. So this identity can also appear in these ways. Alright, very good.
Assuming all quantities are defined, show that 1 over cosec theta is equal to sine theta. Now, before I solve, I want you to note that from the beginning we used COSEC, cosec theta, but then we can equally use CSC for cosec. So if you see CSC, it also means cosec. Okay. Now, cosec theta is the inverse of sine theta. So 1 over sine theta gives us cosec theta. That means that 1 over cosec theta as given is going to be 1 over sine theta. That's what it means. And so we can reciprocate 1 times sine theta over 1. And that gives us sine theta. And it is as simple as that. Show that tan theta is equal to sine theta multiplying sec theta. Okay, solution. So we have tan theta to be equal to sine theta over cosine theta, if you remember. And this expression can be written as sine theta times 1 over cosine theta. And the inverse of cosine theta is sec theta. So we have sine theta multiplying sec theta, and that is verified. Okay, so we are to show that a fraction with numerator sec theta divided by denominator 1 minus tan theta is equal to a fraction with numerator 1 and denominator cos theta minus sine theta. Okay, let's solve. Sec theta over 1 minus tan theta. Now, first of all, I will rewrite them in their original ratios. So sec is 1 over cos theta, and then tan, so 1 minus sine theta over cosine theta. Then I will try to simplify. So for the numerator, I have 1 over cos theta. For the denominator, if I multiply the LCM, I get cos theta minus sine theta all over cos theta. Then I will have to do the division by reciprocating. So 1 over cos theta will multiply cos theta divided by cos theta minus sine theta. So cos theta here cancels cos theta here, and the result becomes 1 over cos theta minus sine theta, and that verifies the question given. Okay. Now, when you are given a question like this, you are not restricted to proving from left to right. At times, you can also prove from right to left. And so I will prove from right to left by taking the right side, and then I will work it to obtain the left side. Okay, so this is what I have. So I'll find my LCM. That will be 1 minus sine theta multiplying 1 plus sine theta. So the numerator will become 3 multiplying 1 plus sine theta, and then minus 3 multiplying 1 minus sine theta. Okay, now I can open the brackets. So I have 3 plus 3 sine theta minus 3 plus 3 sine theta, and my LCM is difference of two squares. That gives me 1 minus sine squared theta. Okay, so now let me add like terms. So 3 minus 3 will go away, and then I'll have 6 sine theta divided by 1 minus sine squared theta. Now, if you remember, I will take you back again. The trigonometric or Pythagorean identity sine squared theta plus cos squared theta is equal to 1. So if I make cos the subject, I'll get 1 minus sine squared theta. So for my denominator here, I'll write it as cos squared theta. So I have 6 sine theta divided by cos squared theta. Okay, and that means I can rewrite this expression as 6 over cos theta multiplying sine theta over cos theta. Okay, so now I want to do the conversion. So I bring 6 out. I have 1 over cos theta, and then I have sine theta over cos theta. And that's I get 6 multiplying 1 over cos theta is sec theta, and then sine theta over cos theta is tan theta. So becomes 6 sec theta tan theta, and that verifies the expression given. That's 3 over 1 minus sine theta minus 3 over 1 plus sine theta is equal to 6 sec theta tan theta. Alright. So also to show that a fraction with numerator sine theta over denominator 1 minus cosine theta is equal to a fraction with numerator 1 plus cosine theta divided by denominator sine theta. Okay, so I'm proving from the left to the right. Sine theta divided by 1 minus cosine theta. What I'll do is to rationalize. So I'll have sine theta over 1 minus cosine theta, and I'll multiply this fraction by the conjugate of 1 minus. So I'll have it as 1 plus cos theta divided by 1 plus cos theta. So when I do the multiplication, I'm going to obtain sine theta plus sine theta cos theta divided by, so this one will be difference of 2 squares, which happens to be 1 minus cos squared theta. Okay. So I continue by converting 1 minus cos squared theta to sine squared theta. So I have sine theta plus sine theta cos theta, and then from the Pythagorean identity, the denominator can become sine squared theta. Okay, now I'll factor sine theta out. So sine theta out, 1 plus cos theta. Then here I have sine theta multiplying another sine theta. So this sine theta will cancel this sine theta, and the result will be 1 plus cos theta divided by sine theta. So we have to show that tan theta plus cot theta is equal to 1 over sine theta cos theta. Okay, so the first thing I will do is to write tan theta as a ratio of sine and cosine, and then cot theta also as a ratio of cosine and sine. So tan theta plus cot theta. This is the same as sine theta over cos theta plus cos theta over sine theta. Then I will find the LCM, which will be sine theta cos theta and then for the numerators I'll have sine squared theta plus cos squared theta. So from the Pythagorean identity, sine squared theta plus cos squared theta is equal to 1. So I have 1 over sine theta cosine theta. That is verified. To show that cot theta plus sine theta over 1 plus cos theta is cosec theta. Okay, so cot theta plus sine theta divided by 1 plus cos theta. This cot theta can be written as cos theta over sine theta. That's the reciprocal of tan, plus sine theta divided by 1 plus cos theta. Now my LCM will be sine theta multiplying 1 plus cos theta. Then my numerator, cos theta, will multiply 1 plus cos theta. Then sine theta will multiply sine theta, which will give me sine squared theta. Okay. Now I will open the bracket and simplify. So I have cos theta plus cos squared theta plus sine squared theta. Everything here divided by sine theta multiplying 1 plus cos theta. So sine squared theta and cos squared theta together will give me 1, which will give me cos theta plus 1. Then divided by sine theta multiplying 1 plus cos theta. Okay, so the numerator and the denominator, what we have in bracket, are equal. And so this one can cancel this, giving me 1 over sine squared theta. Sine theta. And sine theta is the same as cosec theta. Show that sine theta plus cos theta in one bracket multiplies tan theta plus cot theta in another bracket. This will result in sec theta plus cosec theta. Okay, so we have sine theta plus cos theta in one bracket multiplying tan theta plus cot theta in another bracket. So sine theta plus cos theta is multiplying sine theta over cosine theta, which is tan, plus cos theta over sine theta, which is cot. So sine theta plus cos theta. Then I will find my LCM, which will be sine theta cos theta. And then here sine squared theta plus cos squared theta. Okay, now the numerator will become 1. So I'll have sine theta plus cos theta multiplying 1 over sine theta cos theta. And that I'll have it as sine theta plus cos theta divided by sine theta cos theta. And this can be rewritten or can be separated into their partial fractions as sine theta over sine theta cos theta plus cos theta over sine theta cos theta. So sine here will cancel sine here, cos here will cancel cos here, giving me 1 over cos theta plus 1 over sine theta. And 1 over cos theta is given as sec theta, and then 1 over sine theta is given as cosec theta, and that is verified.